Good morning, cadets. We have concluded the topic of thermal properties of matter and we dealt with the thermal energy, right? In this topic, we are going to learn the laws governing the thermal energy. The laws governing the thermal energy, right? In this season of winter, when we rub our palms against each other, we feel warmth, isn't it? The work done against the friction that is developed here on rubbing, the work done is converted into heat. This is what we have already known. In another context, in the case of steam engine, the heat of the steam is used to do the work, conversion of heat energy into work. The heat of the steam is used to move the piston, and in turn the piston is utilized to move the wheels. So heat energy is converted into mechanical energy. So there is an interrelation between work and heat and work. So in this particular topic we are going to understand the meaning of heat, work, temperature, internal energy in detail, where we need to learn carefully what is the meaning of internal energy, what is the meaning of work done, what is the meaning of heat, what is the meaning of temperature in detail. We already know what is the meaning of heat. We are knowing that heat is a form of energy. But earlier, in the 16th, 17th century, heat was considered to be an invisible fluid which flows from a hot body to cold body. That's what we are knowing now, heat flows from hot body to cold body. But earlier it was thought that heat is an invisible fluid which flows from cold body to hot body. This fluid was called as caloric. It was first called as caloric, an invisible fluid present in the pores. Present in the pores, which flows from cold body to hot body when they are in contact. And they are brought in contact. This is the concept of heat. Earlier, concept of heat, which we know in a better manner. The modern concept of heat we are already knowing. It was Benjamin Thompson who was an engineer who was given a task of drilling the holes on a brass cannon. He was given a task of drilling hole on a brass cannon. I think he is a French engineer. While the drill was, when the hole was being drilled, lot of heat was produced, which could be able to boil the water. When they used to put the water, immediately water used to get boiled. So much of heat was produced. Then it was puzzling for him that how is this heat being flowing out? How is that heat is produced? More sharper the drill, more is the heat. That was the earlier concept. But it was not observed so. More the work done by the horses which were employed for drilling the hole, more the work done by the horses, more was the amount of heat produced. So Benjamin Thompson concluded that heat is not the caloric which earlier was thought of to be as a fluid present in the pores of cold body, and it can flow from cold body to hot body. That was the earlier concept. He discarded that, and Benjamin Thompson was awarded Count. He was later awarded as Count Rumford for this new concept of heat. He stated that whenever the work is done on a particular body, the work is converted into, that mechanical work is converted into heat energy, and he stated that heat is a form of energy. So later, from that experience, he stated that heat is a form of energy which transfers. Still we are using the term of flowing. Flow means the one which can flow, means what? It should be a fluid. Still we are using that term, right? Heat is the energy which flows from hot body to cold body. If it is a flowing, means it should be a fluid. That was the earlier concept. Means heat is a form of energy which transfers, which gets transferred, which is transferred. Energy, transferred energy from hot body to cold body. That was the modern concept which was brought, hot body to cold surroundings, by Benjamin Thompson. So he was awarded Count Rumford. Now we are already knowing what is the meaning of heat. Heat is the energy that is in transit. Energy in transit. So we should be very careful in defining what is the meaning of heat, what is the meaning of thermal energy, what is the meaning of internal energy, what is the meaning of temperature. So all these things we are going to learn in this particular topic. Okay. Now, what is thermodynamics? Thermodynamics is branch of physics which mainly deals with work and heat, conversion of mechanical work into heat, conversion of heat into work. Mainly the thermodynamics is developed in order to understand the heat engines, the steam engines, how to improve the efficiency of the steam engines which were invented in that particular 18th century. In order to improve the efficiency of the heat engines, steam engines, the thermodynamics developed. So thermodynamics is a branch of physics. We will define now. It's a branch of physics which deals with heat, work, internal energy, and so on. So thermodynamics is a branch of physics that deals with the concepts of heat and temperature and interconversion of heat and other forms of energy. Interconversion of heat and other forms of energy. As I said, conversion of mechanical work into heat, heat into mechanical work. It is mainly dealing with the concepts of heat and temperature and interconversion of the heat into other forms of energy. Okay. Now it's a macroscopic science. It's a macroscopic science. It does not deal with the microscopic aspects of a system. It does not deal with the molecular constituents of the system. It does not deal with the molecular constituents of the system. In fact, when thermodynamics was developed, the theory of molecular concepts and the microscopic concepts of atoms and molecules was not done still that particular time. The concepts of molecular theory, atomic theory, kinetic theory of gases and all were done in the 19th century. Well before that, the thermodynamics was developed. So it is a macroscopic science which does not deal with the microscopic aspects, that is molecular aspect of the system. Then you see how is that a state, a thermodynamic state is defined. That's very, very important. A gas of a particular system in a thermodynamic state. The thermodynamic state of a gas is defined by macroscopic concepts such as pressure, volume, mass, composition, temperature, and all these. These are called as the thermodynamic state variables of a gas. So it mainly deals with pressure, volume, mass, temperature, composition, which are macroscopic aspects, macroscopic concepts. They do not deal with the molecular picture. So they are dealing for the entire bulk system. So pressure denoted by P, volume V, mass M, temperature T, and composition, and so on. These are all mainly the macroscopic aspects which are called as state, thermodynamic state variables. The thermodynamic state variables are the ones which describe the thermodynamic state of a particular system. It defines what is its pressure, exact value, what is its volume, temperature. So that's how they are called as thermodynamic state variables. Now, when we say that it's a thermodynamics, then we will be thinking of the mechanics what we have learned in the previous part of the physics. Mechanics deals with statics as well as dynamics. Do you remember? So kinematics and dynamics, which mainly deals with motion of bodies, motion of particles and motion of the bodies. Here thermodynamics is nothing to do with the motion of the bodies as a whole. We are not studying the motion of the bodies in this case. What is happening internal in the bulk system? What is happening in the bulk system of a particular gas? We are going to deal in detail. So thermodynamics is a macroscopic science which is dealing with the macroscopic thermodynamic state variables of a system. We have nothing to do with the motion of a system as a whole, motion of a bulk system. Thermodynamics is nothing to do with motion of a system. When there is a motion of a system, then we study mechanics separately. What is happening in the internal bulk system, we are going to learn. For example, when a bullet is shot, when a bullet is fired, the main thing is there is a change in kinetic energy. The bullet gains kinetic energy. So as long as the bullet is in motion, we state it as a mechanics, kinematics, its motion in terms of kinetic energy. When the same bullet enters into a wooden plank, after entering through the wooden plank, it gets stopped through small length, through small distance. But when we go and observe the surface, touch the surface, we will find heat. So what has happened to the kinetic energy of the bullet? The kinetic energy of the bullet is converted into the heat. The work done against the friction inside the layers of the wood, the work is converted into, the work done against the friction is converted into heat. As a result, the temperature rises. So we are dealing with that part. How is that kinetic energy is converted into the rising temperature? How is that leading to rising temperature? There comes the thermodynamics. What has happened to the surrounding layers of the wood when the bullet has passed through? We do not deal with the temperature of the bullet itself. But when the bullet pierces through the wooden plank, there comes the conversion of work done by the bullet against the work done against the friction. How is it converted into heat? Interconversion of mechanical work into heat, heat into mechanical work. How is that? Rise in temperature. There comes the thermodynamics. Okay. Now we are going to define the thermal equilibrium. Now we are going to learn very important thing, that is about thermal equilibrium. What is the meaning of thermal equilibrium? Consider A and B are two systems of gases. A is one container of gas, B is another container of gas, and these gases A and B are having pressure values PA and VA for system A, PB and BB for system B, and they are kept close to each other, separated by a non-conducting wall. It is called adiabatic wall, separated by a non-conducting wall or insulating wall, where there is no transfer of heat from one system to another system. So non-conducting or insulating wall, it is also called as adiabatic wall. When they are separated by adiabatic wall, even the surrounding is also totally insulated, totally adiabatic. Then the pressure volume values and even composition and pressure volume values of the B and composition remain same. When the two systems, even when they are brought close to each other, separated by an adiabatic wall, non-conducting wall, if their pressure volume values remain same over the period of time, then these systems are said to be in thermal equilibrium. So systems A and B are said to be in thermal equilibrium if the thermodynamic variables, or you can say state variables, remain same without changing. So here these systems are separated by adiabatic wall. Systems A and B are said to be in thermal if A and B are separated by adiabatic wall. And adiabatic surroundings. Even the surrounding is also not conducting. Adiabatic wall and adiabatic surrounding. Now let us see another case where system A and B are surrounded by adiabatic surrounding, but A and B are separated by conducting wall. Conducting wall is called as diathermic wall. Then what happens? Then you will find that there will be change in their pressure and volume because of exchange of heat if A and B are separated by a conducting wall. Now consider the second situation wherein the same systems having a pressure values PA and VA and B having pressure value PB and VB are now kept separated by a conducting wall, heat conducting wall, so that heat exchange can take place, and surrounded by adiabatic wall, surrounded by insulating wall. So this conducting wall is also called as diathermic wall. Diathermic means which is ready to conduct the heat. Then after certain time, you see, due to exchange of heat, the pressure and volume values will not remain same. The pressure and volume values will change. PA will change to PA dash. PB will change to PB dash. Similarly, volume may change from VA to VB, BA to BA dash, and VB of the system B will change to VB dash. As a result, the pressure and the volume values will vary from PA to PA dash, PB to PB dash, VA to VA dash, VB to VB dash. Once they vary and remain same, then we say that system A and system B are in thermal equilibrium. So we can write here, if A and B are separated by diathermic or conducting wall, then due to exchange of heat flowing from one system to another system, PA, VA of system A change to PA dash, VA dash, and PB, VB pressure volume of B change to PB dash, PB dash, and then if they remain same, PA dash, PB dash, PA dash, and PB dash, PB dash, then they are in A and B are in thermal equilibrium. So pressure and volume values changed from PA to PA dash, PB to PB dash, VA to VA dash, and VB to VB dash. Then the question arises, when it is in thermal equilibrium, which is that quantity which will remain common? Now we will guess that yes, when two systems are in thermal equilibrium, one particular quantity remain constant. Until that is attained, the systems are in the state of changing. Once that common thing is attained, then they are said to be in thermal equilibrium. That guess is temperature. So in order to arrive at the concept of temperature, we are learning one very important law of thermodynamics, which defines what is temperature. Okay, that is called Zeroth Law of Thermodynamics. Zeroth Law of Thermodynamics defines what is temperature. Now consider there are three systems A, B and C, such that the system A is having pressure PA, VA, and system B is having pressure PB and VB, and the third system C is having pressure PC, VC respectively, such that A and B are separated by non-conducting wall. A and B are kept in close vicinity, separated by adiabatic wall, non-conducting, which doesn't allow the exchange of heat. And A is in contact with C, B is in contact with C by conducting wall. A and C are separated by conducting wall, we can say. B and C are also separated by conducting wall. Then, although A and B, there is no exchange of heat, there is going to be exchange of heat between A and C because of diathermic wall. Conducting means diathermic wall. And exchange of heat will be there between B and C due to conducting diathermic wall. As a result, the pressure values of PA and VA with respect to C will become PA dash, VA dash, and the values of C will be PB dash, PC dash, and BC dash. And then similarly, at the same moment, you see the system B will be possessing PB dash, VB dash, and at that moment it will be having same PC dash and BC dash. Once these variables attain constant values, then we say that A is in thermal equilibrium with C, B is in thermal equilibrium with C. When A is in thermal equilibrium with C and B is in thermal equilibrium with C, then we can say that A is also in thermal equilibrium with B. This is what is known as Zeroth Law of Thermodynamics. If two systems are in thermal equilibrium with the third system, then those two systems are also in thermal equilibrium with each other. This is called as Zeroth Law of Thermodynamics. Then when the pressure and volume values are changed from PA to PA dash, PB to PB dash, PC to PC dash, once they attain the constant values, although we say that they are in thermal equilibrium with each other, then what is common? Common thing is the temperature. Due to exchange of heat, you see the temperature of A, if it is A, and temperature of C, if it is C, then when A becomes in thermal equilibrium with C, then TA becomes thermal equilibrium with C, then TA becomes equal to TC. Exchange of heat between A and C take place because of conducting wall, because of diathermic wall, until the temperature of A and C attain same value. Similarly, B is also separated by conducting wall with respect to C. In this case, if it is TB and if it is TC, B and C are going to attain thermal equilibrium if the temperature of B and C become equal. When the temperature of system B and system C becomes same, TB equal to TC, then we say that B is in thermal equilibrium with C. When TA is equal to TC, TB is equal to TC in thermal equilibrium, then obviously TA is equal to TB. This is called as Zeroth Law of Thermodynamics. So we will write here. If two states are in thermal equilibrium, with the third state. So, if two systems are A and B are in thermal equilibrium with the third system C, if two systems are in thermal equilibrium with the third system C, then those two systems A and B are also in thermal equilibrium separately. So this is called Zeroth Law of Thermodynamics. Statement of Zeroth Law of Thermodynamics. Then what do we observe here? The main thing that will be observed here is one common thing, that is temperature of all these three systems become same. When TA becomes equal to TC and TB becomes equal to TC, then according to the statement, TA becomes also equal to TB. So that's how we define temperature is defined using zeroth law of thermodynamics. Now, even if you exchange now, suppose now I am taking this A and B separated by conducting wall, and C is separated by adiabatic wall now. But already A is in thermodynamic equilibrium with C, B is in thermodynamic equilibrium with C. So even if you separate A and B by a conducting wall, there is no exchange of heat. I think you got the point. Suppose now in the second situation, what I will do, this adiabatic wall I am replacing it by conducting wall, and this conducting wall is now separated by non-conducting adiabatic wall. Already A is in equilibrium with C, B is also in equilibrium with C. So even if now A and B are separated by conducting wall, there is no much further exchange of heat taking place, since they are already in thermal equilibrium. So thermal equilibrium is that state at which the temperature of the systems will be same. The temperature of the systems remain same. When the temperature of the systems becomes same, then they are said to be in thermal equilibrium. This is how we define temperature using zeroth law of thermodynamics. So zeroth law of thermodynamics defines what is temperature. Temperature is that common feature of two systems in thermal equilibrium. When these two systems attain thermal equilibrium, they possess common temperature and there is no much further transfer of heat. And we know that as long as there is a temperature difference, there is a transfer of heat from a system at high temperature to a system at low temperature. As long as temperature difference exists, there is a flow of heat, there is a transfer of heat from a system at high temperature to a system at low temperature. So once both the systems attain same temperature, there is no further flow of heat, there is no exchange of heat. This is the meaning of the zeroth law of thermodynamics. In the next video, we will learn in more detail about what is heat, what is work, what is temperature, what is internal energy in detail. Thank you. Have a nice day.